In this video, we're going to focus on a problem that will require a good understanding of quantum numbers for an electron in an atom, wave functions, orbital shapes, and the radial distribution function. So let's first by stating the problem. The picture on the left below shows the general shape of an orbital. The picture on the right below shows the radial distribution function for that same orbital. Identify the shell and the subshell of that orbital. So obviously we're going to have to understand orbital shapes, radial distribution functions, shells, subshells, and quantum number labels to be able to solve the problem. Now all of that comes from the general idea of quantum theory and the idea that the electron shares many characteristics of a wave in its behavior in the atom. Now, there was no better illustration of the wave behavior of electrons than what we saw in class, where an electron behaves in a double slit experiment almost exactly the way light waves behave. Now, light waves, when they impinge on a double slit, you'll see the two beams of light emerging from the other side of that slit. Those two beams will interfere with each other, and you'll see a light-dark pattern on a screen where the light hits behind the double slit. If you do the same thing with an electron, you get exactly the same behavior. In other words, the electron appears to interfere with itself, which is exactly what you'd expect from wave behavior. So going back to the 1920s and the Schrödinger equation, we now have a mathematics set that can apply this idea of waves and calculate very precisely the energy levels and wave functions of an electron, particularly in simple atoms like hydrogen. So the way we're going to start to develop quantum theory is to go back to a very simple analogy, namely that of a vibrating string. So let's look first at what happens when a guitar string or a cello string is struck or bowed. You get a vibration that results in a specific musical note that's transmitted to our ears. And the reason for that is that the string is only vibrating at very specific frequencies, corresponding to the length of that string and some of its other properties like thickness, etc. And the reason we just hear a specific musical note and not just a cacophony of notes is that when the string is plucked, only specific waves survive. And the reason for that is that the string is physically constrained at both ends. It's tied down on the left, it's tied down on the right. So just specific waves we call standing waves will survive, and those waves are those that have exactly zero amplitude at either end of that string. So if we look at the first of these waves, what we see is that the length of the string is equal to 1/2 the wavelength. I have another one. The next one is where one wavelength is equal to the length of the string. The next one, I have 3/2 of a wavelength equal to the length of the string, and etc., going in half integer multiples from here. And you see that each of these waves has exactly zero amplitude at both ends. Now, this is analogous to the quantum behavior of the electron in an atom. And the reason we get that quantum behavior in the atom is because the electron is similarly constrained. It is attracted to the positive charge of the nucleus, so the electron is physically constrained in space to be close to the nucleus. And when we solve the Schrödinger equation for an electron, negatively charged electron, near a positively charged electron, what we get is not just any possible energies or any possible wave shapes for that electron, but only specific ones, just like we get for the plucked string. So we don't have to solve the Schrödinger equation or really understand the mathematics to look at the result. So what we're going to focus on here is what is the outcome of solving the Schrödinger equation for an electron near a central positively charged nucleus. Now, just in the vibrating string, we can describe the energy levels for the electron by a set of integers, 1, 2, 3, etc. And those appear like this as a series of energy levels, 1, 2, 3, 4, 5, 6, and as n increases, the energy of those levels goes up as well. But this isn't the only set of quantum numbers that are required to completely define how an electron appears in an atom. What we know is that each of these energy levels has a sublevel beneath, which means I need another set of quantum numbers. And in fact, I need 4 sets of quantum numbers to fully define any electron in an atom. So let's go to the next level down, and within each of these primary energy levels, specified by the primary quantum number n, we know that sublevels exist, and we're going to give that quantum number for those sublevels the lowercase l as its symbol. And what we find from the wave equation is that L can have any values ranging from 0 to n minus 1, or rather any integer values from 0 to n minus 1. So if we start with the lowest level, which is n equals 1, and going up all the way, we know that each of those sublevels is going to have a possible sublevel of L equals 0. That's always going to be possible for every single level in the electron. For n equals 1, however, let's look at any possible additional L levels that might result. L equals 0 is good. We know n equals 1, and we know the maximum value of L is n minus 1. n minus 1 is obviously 0. So for the case of the n equals 0 level, the only possible sublevel I can have is actually just L equals 0. Now let's go to n equals 2 and see what happens. I not only have L equals 0 as a possible sublevel, but I can also have L equals 1. Why is that? Because the maximum value of L is equal to n minus 1. When n is 2, 2 minus 1 is 1. So I can have these two sublevels, both L equals 0 and L equals 1. And that same behavior continues. If we look at what happens when n equals 3, L can be 0, 1, or 2. Obviously, the maximum value of L is 2 because when n equals 3, 3 minus 1 is 2. When n equals 4, I can have L equals 1, L equals 2, or L equals 3. When n equals 5, I just keep this trend going. I can have L equals 0, L equals 1, L equals 2, L equals 3, or L equals 4. Now, the quantum number L corresponds to the subshell designation that chemists still use. Now, the shell-subshell behavior is sort of reminiscent of the now defunct Bohr model of the atom, which was our first attempt back in the early 1900s to understand the quantum behavior that the electron was exhibiting at the time. And that label that we use for the subshell in the atom, the SPDF label, goes all the way back to the 1870s. So as we oftentimes find in chemistry, we latch on to labels and notation for historical reasons, and it doesn't change. So these L sublevels correspond to the subshell that we're already familiar with in the model from introductory chemistry. So L equals 0 is the S subshell, L equals 1 corresponds to the P subshell, L equals 2 corresponds to the D subshell, and L equals 3 corresponds to the F subshell. Now, what about for L equals 4? Now, from what we know from our introductory chemistry, the only subshells we ever dealt with were S, P, D, and F, and there's nothing beyond that. Now, the reason for that in chemistry is that there's no known atom that exists yet or has even been made in the laboratory where we actually need an L equals 4 quantum number or any L quantum number higher than 3. So normally we wouldn't talk about that, but there is, in fact, possible an L equals 4. And if we were ever to make such an atom in the laboratory, we would call that the G subshell. So just understand that this set of quantum numbers and subshells does exist, but we actually don't use it because it's just not required in chemistry. So let's just get rid of that designation and stick to the range of L's that we know we'll need to deal with. 0, 1, 2, and 3 corresponding to S, P, D, and F. Now again, that's not the entire story. There's another set of quantum numbers in addition to L, and those correspond to a series of orbitals that exist in each one of these subshells. So what the Schrödinger equation tells us is that it's oftentimes possible to have more than one orbital in a given subshell. So those orbitals we're going to label with the quantum number m sub L. And m sub L, again, is going to be an integer, which can assume any value from minus L to plus L. So let's look at how that's going to behave. We'll start at n equals 1. The only possible subshell is L equals 0. We know that m sub L can range from minus L to plus L, but since L is 0, the only possible value of m sub L is 0 as well. And because of that, we know that this n equals 1, L equals 0 subshell can only have one orbital. And we're going to show the orbitals here on our diagram as a box. So let's put that box in here, label it with m sub L equals 0. Let's get rid of the line. So now we show our orbital for n equals 1, L equals 0, and m sub L equals 0. Now let's go another level up to n equals 2. Again, when L equals 0, the only possible value of m is 0, so let's show that one orbital. But when L equals 1, I can have three orbitals. M sub L equals minus 1, 0, and plus 1. In other words, ranging from minus L to plus L. So for any of my L equals 1 subshells, I'm going to have three orbitals. Let's get rid of the lines again. So there's our orbitals that exist for n equals 2. When n equals 3, I have those same possibilities. Again, one orbital for L equals 0, three orbitals for L equals 1, but now for L equals 2, I can have 5 values of m sub L. So in other words, 5 orbitals exist in that n equals 3, L equals 2 subshell right here. And the m sub L values are minus 2, minus 1, 0, plus 1, and plus 2. All right, let's keep going because the same trend continues. When we go to n equals 4, I have the same behavior, but now let's look at what happens when I reach all the way out to L equals 3. Now I can have 7 possible orbitals. M sub L going from minus 3 to minus 2 to minus 1 to 0 to plus 1 to plus 2 plus 3. And the same behavior is going to be seen when n equals 5. Again, if we were to need to go to L equals 4, you can easily imagine how many orbitals that might have. So think about that and see if you can figure out how many orbitals would exist whenever I have an L equals 4 subshell. So a good exercise to think about. That's not the full story. As we said, I need one additional set of quantum numbers. And what we know is that from the Schrödinger equation is that each orbital can have a maximum of 2 electrons. And we'll designate those 2 electrons as having one of 2 additional quantum numbers, which we'll label m sub s. Those values are minus 1/2 or plus 1/2. What the Schrödinger equation tells us is that the electron has an angular momentum property, or sometimes what is called spin. And that's unfortunate because it seems like it would imply that the electron is like a spinning top, which is a pretty overly simplistic view. But nonetheless, what the Schrödinger equation tells us is that if I indeed have 2 electrons in an orbital, then one of them will have the minus 1/2 m sub s quantum number, and the other one will have the plus 1/2 m sub s quantum number. The way we'll show the electrons in our orbital box energy diagram is we'll show them as arrows. So if I have 2 electrons in an orbital, I will have one electron that I show as an up arrow, as I'm showing here in the bottom left level, and the other will be an arrow pointing down. So I'll get behavior that looks like this. Now there's no specific designation that says the up arrow has to correspond to either minus 1/2 or plus 1/2, or the down arrow the other. And if there's only one electron in an orbital, it's pretty typical for the diagram to show an up arrow representing that electron. But again, that's not required. So just understand that these arrows are meant to represent that those m sub s quantum numbers are opposite in sign, but not that we designate either one of them as having a specific value. There's one last thing that we're going to have to do before we leave this particular picture of quantum numbers and energy levels in the electron. And that is to acknowledge that the diagram we've shown thus far is appropriate for the hydrogen atom, which has just one electron orbiting the nucleus. If I have more than one electron, the results get a little bit more complicated because each of these subshells does not have the same energy within a given value of n. So let's develop that last piece of complexity. To do that, we're going to shrink this diagram down a little bit, get rid of some of the extraneous labeling. So let's shrink that diagram down and look what happens when I have more than one electron in the atom. What happens is that the L equals 1 level is shifted upward in energy relative to the L equals 0 sublevel at each of those energy levels n. The L equals 2 sublevel is shifted up a little more, and the L equals 3 sublevel is shifted up a little bit more than that. The result of that is that I find eventually that the orbital levels start to overlap one another. A good example of that is if I look at the 3D level, which is now right here. The 3D level actually lies a little bit higher in energy than this 4S level. Notice that the 4D level right there lies a little bit higher in energy than the 5S level, and etc. So some of the energy orderings can get kind of complicated, and we discussed in class how to understand that by using the periodic table blocking SPD and F. So that's a topic for another discussion. But I just wanted to make sure we understand that this diagram we're showing here is much more appropriate to the many electron atom and more generally applicable. Now let's start looking at the wave functions. Thus far, all we've looked at are the quantum numbers and the energy levels and where the electrons sit. But what we haven't done is looked at the actual wave functions themselves. Now, there are multiple ways to look at the wave functions. The place we're going to start is to look at an overall shape of the orbitals in the atom. And what we find is that the shape or the overall envelope of that wave function changes depending on the value of that L quantum number or the value of the SPDF subshell. So for example, if we look at the shape of the s orbital, it's spherical. Now let's really make sure we understand exactly what that means when we say a spherical shape. Remember that we only know where the electron exists in the atom with some sort of fuzzy probability. So what this shape is meant to represent is a volume in which we are 90% certain the electron exists. Better way to say that is within this particular sphere representing the s orbital shape, I know with 90% certainty that the electron is somewhere inside there. The nucleus always sits at the center of each of these diagrams, in other words, at the origin of each of our axes, x, y, and z. So all the s orbitals will have this general spherical shape. We'll talk about complexities and added on to that shape in a bit. Let's look at our general shape for orbitals with L equals 1. The p orbital, corresponding to L equals 1, has a basic dumbbell shape where I have two lobes, one on one side of a plane and one on the other. And the area where the shape goes exactly to 0 is right at the nucleus. In other words, the point between those two lobes of the orbital. And this is what we call a nodal plane, meaning that the value of the square of that wave function representing that probability falls to 0 at that point. And what we know is that there's a 90% probability that the electron lies somewhere inside of this volume. Notice there's a few things that we can't really understand by taking a classical view of the electron as being some sort of tiny particle of matter like a marble. If there's zero probability of the electron ever being at that nucleus, how does it get from one lobe to the other? And that's not really a question we can even answer. All we know is the probability is 50-50 of the electron being in one lobe or the other, but we don't know more than that. So there's really no easy way to understand in terms of the behavior of a particle or a BB or a marble, how the electron gets from one side to the other. It's just not even a question we can possibly answer. And what we know is that that's not really the right way to think about the electron. The electron is not going to behave like a tiny marble. In fact, it's not completely going to behave like a wave. It's an electron which exhibits properties of waves and also properties of matter or tiny marbles, but is not easily characterized as one or the other. Let's go then to L equals 2, which is the set of d orbitals. The d orbitals have a kind of cloverleaf shape. So there's 4 lobes, and we see that there's now 2 nodal planes. Again, the nucleus sits at the center of this plot, and the electron in a d orbital has a 90% probability of being inside this overall volume that we show somewhere. And the last thing is the f orbital. That looks like some kind of wild balloon animal that has 8 lobes and 3 nodal planes. And you can see the sequence. We go from the s orbital, not showing any lobes, but just a sphere. The p orbital showing 2 lobes, the d orbitals 4 lobes, and the f orbitals 8 lobes. And this, again, just comes completely from the Schrödinger equation mathematics and is the outcome derived from that mathematics. So understand that what these orbital shapes represent is a 90% probability volume, meaning there's a 90% probability the electron will be found somewhere inside of the volume that we're showing here. All right, let's take our knowledge a step further. There's a limitation to these probability envelopes or probability volumes, showing here the s and the p orbital general overall shape. They're sort of like translucent bottles. We can't really see what's going inside of them. All we know about the wave function is that there's a 90% probability that the electron exists in those volumes somewhere, but not any more than that. What we'd like to have is some more information about the shape of the wave function itself. What does the intensity of that wave function look like as a function of distance from the nucleus? So what we're going to focus on is now something we're going to call the radial distribution function. So for example, let's say that we look at just this section of our sphere. So along the z-axis and extending out along the x-axis. So we're just going to look in this particular quadrant. And what we're going to look at is what is the intensity of the wave function as a function of distance from the nucleus. Now what we're going to do is to examine the p orbital set. So we'll be focusing on the wave functions of the first 4 p orbitals in the atom. So we'll get rid of our s orbital here. So what we're going to be doing in this case is looking at what happens to the wave function in this particular area right there. And we'll look at also extending to the negative of the x-axis in this direction also. So the first p orbital is this one. This is the wave function itself. So in this particular plot, the origin, which is right here, is going to represent the nucleus, and the positive x direction, and I'm going in the negative x direction. You see that the wave function is symmetrical in both directions. The y-axis here is actually the intensity of the wave function. So we can see that the intensity of the wave function is 0 at the nucleus, as we expected from that probability envelope. And we see that the probability of finding the electron at a distance r from the nucleus is maximum right there on the positive side and right here on the negative side. As I go further from the nucleus, it's less likely that I'll find the electron at a further distance, and finally, as I approach farther distances from the nucleus, the wave function actually falls to 0. Remember that the square of the wave function represents the probability of finding the electron. So we're going to square these wave functions in a moment, but for now, let's just look at the wave functions themselves. So this is our lowest energy, or 2p orbital. Remember, there is no p subshell for the n equals 1 level. So let's look at the shape of the wave function for the 3p orbital. And notice that this one is a little bit different. I have the same overall shape in that there's a 0 value of the wave function right here at the origin, representing the nucleus. I find a peak of the wave function on either side of that, but notice that after reaching a maximum, the wave function goes below 0, so I have a section of the wave function down here, and then it rises back up and extends back to the baseline as I go further away from the nucleus. So in the 2p case, I see only one crossing of the x-axis by the wave function right here at the origin. With the 3p orbital, I see a crossing at the nucleus. I see another crossing here, and I see another crossing of the nucleus, or the x-axis there. So there's more swings from positive to negative in the 3p wave function than there is in the 2p wave function. Let's look now at the 4p wave function, and this trend continues. Again, the wave function goes to 0 at the nucleus, which is the origin of the graph. It peaks shortly on either side of the origin. And now this time I cross the x-axis at the origin here, another time there, another time here. In this direction, I cross here, and I cross here. So now in the 4p wave function, I actually cross the x-axis 5 times. In the 2p, I crossed once. In the 3p, I crossed the x-axis 3 times. And in the 4p, I crossed the x-axis 5 times. And you can see kind of a trend developing here. Let's look at our last example wave function. We're going to get rid of this probability envelope, and let's put up the wave function of the 5p orbital. Now, remember, we had one crossing of the x-axis here, 3 here, and 5 here. So if that trend continues, we would expect the wave function for the 5p orbital to cross the x-axis 7 times. In fact, that's what we see. So we see it crossing here at the origin. We see it crossing here, so 2, 3, 4 times. On this side, that would be the 5th crossing, 6th crossing here, 7th crossing there. And notice that the energy goes from left to right, 7 crossings of the x orbital, or the x-axis. So notice that as I increase in energy, going from 2p to 3p to 4p to 5p, my wave function crosses the x-axis multiple times. Now that, you may remember, looks very much like the result we saw for the vibrating string. Let's put up the first 4 levels for the standing waves of a vibrating string. This is the lowest energy one here on the left, and it doesn't cross the x-axis at all, except at those fixed points. And we know that in this example of a vibrating string, the string is actually tied down or fixed in space at either end. So we're not going to consider these endpoints as actually crossing the x-axis. If I go to the next higher energy, I go through a full wavelength, and I have one crossing of the x-axis there. If I go to the next higher in energy, I see now 2 crossings of the x-axis. And I go to the next higher energy one, I see 3 crossings of the x-axis. So in a sense, the wave function plot of distance from the nucleus versus energy, or versus the intensity of the wave function, very much looks like the standing waves on a string. As I go higher in energy, I have more crossings of the axis. And what we're going to do with that information is to now look at the square of the wave function, and we're going to only look at a piece of it. So what we're going to look is what we call the radial distribution function. So if we show what we're going to see, we want to look at the square of the wave function, and we're only going to look at this particular area right here in this quadrant. Now, if I square the wave function, any area that's negative becomes positive. So in fact, the wave function, when I square it, has the same appearance on the positive x-axis as it does on the negative x-axis. So there's really no point in considering both. What we're about to show will be a mirror image on both sides. So we're actually going to start our radial distribution plots at the nucleus and just increase in one direction, which we'll call the general direction R. Now first we're going to look at the radial distribution functions for the set of L equals 0 sublevels, which is corresponding to the S subshell. So we'll start by looking at the square of the wave function as a function of distance from the nucleus. This is for the 1s. So you can see an envelope where there's 0 probability of finding the nucleus or finding the electron at the nucleus right here. At a certain distance from the nucleus, I'm a maximum probability of finding the electron. And as I go further out, the probability of finding the electron at this distance from the nucleus is really almost 0. Now remember, what these radial distribution functions represent is truly the probability of finding the electron at a certain distance from the nucleus. The probability is greatest here, falls to 0 at the nucleus, falls to 0 at a far distance from the nucleus. Let's look now at the radial distribution function, meaning squaring the wave function, as a function of distance from the nucleus for the 2s level. And here's what we see. Now remember, as just with the p case, what you see now is that the radial distribution function for the 2s orbital actually touches the x-axis somewhere between the nucleus and far away from the nucleus. And as with the 1s, the radial distribution function for the 2s orbital goes to 0 at the 2 extremes. Let's look at the 3s orbital. As you might expect, it looks like this, where I now have the probability of finding the electron going to 0 here and to 0 there. So as I go to higher and higher S energy levels, meaning 1s to 2s to 3s, I go from 0 touching of the x-axis between the extremes to 1 to 2. All right, that's our set of L equals 0 sublevels, or the S subshells. Now we're going to do the same thing for the set of P subshells. So we'll do L equals 0. So one last thing about the way we're going to refer to these points where we touch the x-axis in between the 2 extremes. We're going to call these radial nodes, meaning points where the function goes to 0 or touches the x-axis. So for the L equals 0 3s orbital, I have 2 radial nodes. For the 2s orbital, I have 1 radial node. And for the 1s orbital, I have 0 radial nodes. Let's look then at the P set. So for L equals 1, the lowest energy possible orbital with L equals 1, the p orbital set, will be 2p. Remember, there's no such thing as a 1p. It looks pretty much like the 1s orbital, meaning I have a 0 probability of finding the electron at the nucleus, the origin of the graph. I have a 0 probability of finding the electron at a far distance from the nucleus. I have a peak of maximum probability of finding the electron at some distance from the nucleus, but at no point in between the extremes does the square of this wave function touch the x-axis. Let's look at what happens to 3p. And now I see a pattern similar developing for the L equals 1 set of orbitals. So the square of the wave function now touches here. So we would call this a radial node. For the 4p level, I touch the x-axis twice. So much as in the L equals 0 case, I have 0 radial nodes for the lowest energy set down here, 1 radial node for 3p, 2 radial nodes for 4p. And if I were to extend this to 5p, as you might expect, there would be 3 radial nodes. If I went to 6p, there would be 4 radial nodes, etc. So this trend continues. Let's move then to the set of orbitals where L equals 2. In other words, the d set of orbitals or the orbitals in the d set of subshells. The lowest energy available d orbital is a 3d, and it looks like this. Now, we've had to actually compress the distance, so certainly we know that the 3d orbital is much further away from the nucleus. So remember that our radial scale is not shown to scale. So it's not true that the 3d orbital is more compressed towards the nucleus than the 3p orbital, or more compressed toward the nucleus than the 1s orbital. So again, notice that these are not to scale along the r-axis. So I have my 0 probability of finding the electron at the nucleus. I have a 0 probability of finding the electron far away from the nucleus. I have a maximum in probability at a certain distance from the nucleus. But at no point in between the extremes does the square of the wave function touch the x-axis. Let's look at the next one, 4D. I have 1 radial node here. 5D, I have 2 radial nodes. So this trend is repeated again, just as it is for the L equals 0 set of orbitals, the L equals 1 set of orbitals. So in general then, we can see the same behavior repeated, and we can come up with an equation which links the number of radial nodes to the 2 quantum numbers n and L. The number of radial nodes will equal the n quantum number minus the value of the L quantum number minus 1. For example, let's look at the 4D level. For 4D, n equals 2. L, because it's a D subshell, L also equals 2. If we plug that into our equation, I have 2 minus 2 minus 1, and the number of radial nodes is then 1. Let's take an example. Let's look at the 4D level. So for this particular case, n equals 4. Because this is a d orbital, L equals 2. Plugging that into our equation, I have 4 minus 2 minus 1. When I do that math, I find that the number of radial nodes equals 1. And that's indeed exactly what we see. So this is a very simple equation which relates the number of radial nodes in this radial probability distribution function to the quantum numbers n and L. Now notice what we're not calling a radial node. We always know that at the origin, this probability function goes to 0. And at a far distance from the nucleus, the probability function again goes to 0. So just as with the vibrating string, we're never going to consider those to be radial nodes. It's only the areas where the function touches the x-axis between the extremes that we're going to consider radial nodes. So in this case, we see 2 radial nodes. We would not say that there's 4 radial nodes for that 5d orbital. Okay, with all of that background, let's go back to our original problem. So just to restate the problem, the picture on the left below shows the general shape of an orbital. The picture on the right below shows the radial distribution function for that same orbital. Identify the shell, or the principal quantum number n, and the subshell, s, p, d, or f, of that orbital. Well, let's start with the picture on the left. I see an overall 4-leaf clover shape, so immediately I know that corresponds to a d orbital, meaning that L equals 2. So that's fairly easy. I can establish that right away. If I look at the right side, what I see are 2 radial nodes, here and here. Again, we're not going to account that as a radial node. We're not going to count this as a radial node. So overall, in this radial distribution function, I see 2 radial nodes. So I can use that information then, since I know L equals 2, and I know the number of radial nodes, I can plug into this equation right here, and I can solve for my value of n. So let's do that. We're going to plug in the number of radial nodes, 2. We're going to plug in our value L, which is 2. So if I solve that equation for n, I find that n equals 5. So for n equals 5, this is a d orbital. I know that my final answer is that these 2 drawings together represent a 5d orbital. Let's do one last problem which is somewhat related, and that's where we're going to take a different type of diagram which attempts to take that overall orbital shape and to put a little bit of extra information on top of it. And in this particular shape, what we're trying to do is to show the radial nodes as well as that central nodal plane. So let's take a look at the problem we're trying to solve. The picture below represents an orbital shape representing the 90% probability boundary for the square of the wave function. The picture shows both nodal planes and radial nodes as color changes. Identify the n and L quantum numbers of this orbital. Well, let's see how we would approach solving this problem. As with any orbital like this, the center is going to represent the nucleus. So I know the nucleus is at the center, and I have from there an overall dumbbell shape, meaning a lobe extending above my nodal plane and a node extending below the nodal plane. And one last note about a nodal plane. We only use the word nodal plane to refer to a plane where there's 0 probability of finding that electron at the nucleus. So a nodal plane is never going to cross the wave function at a distance from the nucleus. A nodal plane is only going to exist at the nucleus. And you can see that on the bottom side I have this kind of brown color, and above I have this blue color. That color change representing a change or a crossing of some sort of plane of 0 probability. Well, now I don't really have a radial distribution function, but remember when we do radial distribution functions, we just look at 1/2, either positive or negative. So I'm just going to consider this part of the picture from the nodal plane on up. What I see is that there is an additional color change at a distance from the nucleus. That occurs right here, and when that color change happens, you can see that the square of the wave function representing this overall shape goes to 0. So I have one radial node here. One nodal plane, an overall p orbital shape, and one radial node. So I have enough information to then figure out what my n and L quantum numbers are. Now I already know, because of the general dumbbell shape and one nodal plane, that L equals 1. And then I can use my equation relating the number of radial nodes to the quantum numbers n and L to solve for n. So let's plug in. I have one radial node. My L value equals 1. So n minus 1 minus 1 is equal to 1. So when I solve that equation, I find that n equals 3. So for this particular orbital, my final answer is that n equals 3 and L equals 1.